This section is about equilibrium. When you first put a reaction together, only the forward reaction starts. Since there are no products, there are no reverse reaction. It can only go one way. It can only go the way we're used to, going towards the products. But as the forward reaction keeps going, the products are going to start building up. And so they're slowly going to be going backwards. So they're going to then make there be more products, and the forward reaction also slows down because it's going to have this other one. And the products are going to build up, and the reverse reaction continues to speed up. So the forward reaction slows down, and the reverse reaction speeds up. Eventually, you're going to reach a point where the reverse reaction is just as fast as the forward reaction. This is dynamic equilibrium. The rate of the forward reaction is equal to the rate of reverse reaction. This is where we have an equilibrium. The concentration of the products and reactions are basically going to stay the same, but the reaction is still running. So the products and reactants aren't going to change concentration because they're going forwards and backwards at the same rate, but they're still changing. So, equilibrium position. Equilibrium position tells you how much product and reactant are at equilibrium. So we show this with the double arrow. This is what we're going to put now in our reaction. Instead of just a forward boring arrow we've had before like this, we're now going to have a double arrow going back and forth. It kind of looks like our electron arrow on the side, which is a half of an arrow, but that is what they look like. These are our equilibrium arrows. So a catalyst can speed up both the forward and reactions, but do not affect the equilibrium position. So you're still going to have the same amount on both sides. So how do we measure equilibrium? So at equilibrium, the concentration of products and reactants are constant. They do not change. We can write a constant that tells us what the equilibrium is. So EQ is what we call an equilibrium constant. It's KEQ. We usually use K for constants. So KEQ equals the products raised to a coefficient all over the reactants raised to a certain coefficient. So the square brackets simply mean the molarity, or the concentration of the solution, moles per liter. All right, let's look at this. So here again is our general equation. We have little a, big A, plus little b, big B. And then we have our forward and backwards arrows now. And then little c, big C, plus little d, big D. The little ones again mean moles. And then the capital ones simply mean the component or the compound we're talking about. So here's how we would calculate the equilibrium constant. You have it equals to the product, so the C and D's in brackets, the concentration of those, raised to the number of moles that you have, the concentration, all over the concentration of A and B, your reactants, raised to their moles. So now let's write the equilibrium expression for the following reactions. We now want to put our products on top, so we're going to put our NH3. We're going to raise that to the second power because there were two of them. We're going to put that all over. We then have H2, so we're going to put H2 in brackets. And we have three of those, so raised to the third power. And then we're going to multiply that by the concentration of N2. And we only had one of those, so raised to the first power. That would be how we'd write an equilibrium constant. We'd have to know the concentration of these things to move forward. The next reaction we're going to have is right here. So we have two products and one reaction. So we're going to take our H2, square it, and then multiply that by O2. And we're just raise this to the first. You don't have to write the one, but it is useful. We're going to put that all over. And again, we have two waters. And we're going to raise that to H2O squared. So that's how we write equilibrium constants. So how do we calculate equilibrium? So again, the K equilibrium, or the equilibrium constant, is the only affected by temperature. It's the only thing that can change it. So we can calculate the equilibrium constant for the following reaction. We have 3H2 plus N2 reacts to make 2 ammoniums if at 25 degrees Celsius there are 0.5 moles of N2 and 0.25 moles of NH3 and 0.10 moles of H2 in a 2-liter container. All right, we have our moles and we have our volume. So what we need to do is figure out our molarity. So we're going to take our 0.15, divide that by 2, and then we're going to take, which will equal our molarity, then we're going to take 0.25, divide that by 2, that will give us our molarity as well, and then also 0.10, divide that by 2, and that will give us our molarity as well. Okay. All right, let's start over again.